Lake Tahoe's water level has dropped to a 4-year low. One researcher says the water level is decreasing about 1/4 of an inch a day. That's something to certainly keep your eye on.
For a lake long marketed as almost unreal in its clarity, the shift is unsettling. In Lake Tahoe, water levels rise and fall every year, but in the recent dry cycle, water levels are dropping fast, and divers found something horrifying. Under the surface, the lake has always held traces of its past, but as levels fall, those traces move closer to light and visibility, turning ordinary recovery work into something that feels more like excavation. Above the water, Lake Tahoe appears unchanged, bright, deep blue, framed by the Sierra Nevada. Below and along the receding edge, the exposed lakebed is a haunting sight. Today, we'll explore all the horrors. Physical debris and submerged human objects. The first things they find are never the things people imagine when they think of a pristine alpine lake. Divers working systematic cleanup routes along popular access zones, especially near South Lake Tahoe, Tahoe City, and Emerald Bay, regularly recover bottles, aluminum cans, fishing line tangled into submerged root systems, and fragments of recreational gear lost during decades of tourism pressure. The scale is not cinematic, but cumulative. Thousands of individual items documented over repeated seasonal dives rather than single dramatic discoveries. As the work expands deeper along steep underwater slopes, the debris changes character. Tires appear lodged in sediment pockets, likely discarded during the mid to late 20th century when environmental enforcement was minimal, and dumping practices were poorly regulated in many parts of the United States. Bicycles show up twisted in rock crevices, sometimes intact enough to identify modern components, sometimes reduced to corroded frames that suggest decades of submersion in cold, oxygen-poor water that slows decomposition. The lake does not erase objects quickly. It preserves them in a suspended state where time moves more slowly than on land, but never stops entirely. Then come the vehicles, and the record becomes sharper. In several documented recovery operations and dive surveys, older automobiles have been located near steep drop-offs and historic access points, places where unpaved roads once ended abruptly at the waterline. Many of these vehicles are estimated to date from the 1940s through the 1970s, a period when shoreline development expanded rapidly around the basin and environmental controls were still evolving. Some appear to have rolled or been pushed into the lake accidentally. Others were likely disposed of intentionally. At depths where light fades and sediment softens into fine silt, these submerged objects take on an almost archaeological quality. Cold water temperatures in Tahoe's deep zones, often hovering near 4 degrees Celsius or 39 degrees Fahrenheit, reduce bacterial activity, meaning materials like paint, rubber, and even upholstery can persist far longer than in warmer lakes. That is why some recovered vehicles still retain visible structural outlines. Doors, dashboards, and frames remain recognizable even after decades underwater. It is not preservation in the romantic sense, but in a physical, chemical slowdown that traps objects in time. Beyond debris fields, the lake also contains deliberately recorded wreck sites that are part of its documented underwater heritage. In areas such as Emerald Bay, submerged wooden vessels dating back to the late 19th and early 20th centuries rest on the lake bed, cataloged and mapped rather than discovered by chance. These sites are protected and studied, offering controlled glimpses into early tourism and transport history in the basin. Cold, low oxygen conditions have allowed hull structures to remain partially intact, turning the lake floor into a quiet archive of regional development. But what makes Lake Tahoe unusual is not the presence of objects. It is their distribution and persistence. Unlike rivers that flush debris downstream or warmer lakes where biological decay is rapid, Tahoe's clarity and stratification allow materials to remain visible in place for decades without disappearing from the system. Each recovered item, whether a bottle from a beach or a vehicle from a submerged slope, is less an isolated find and more a timestamp of human activity layered across time. But it only gets scarier from here. Nutrient loading and eutrophication pressure. At first glance, nothing about Lake Tahoe suggests imbalance. The surface is famously transparent, often allowing visibility tens of feet down, a rarity among large lakes. Scientifically, it is classified as an oligotrophic system, meaning extremely low in nutrients, especially nitrogen and phosphorus. But that classification is also the warning label. In such systems, even small nutrient changes are enough to shift biological behavior in measurable ways. The main inputs begin far from the open water in the surrounding 506 square mile watershed that drains into the lake. Stormwater runoff carries fine sediments and dissolved nutrients from paved roads, parking lots, and residential zones in communities like South Lake Tahoe, Incline Village, and Tahoe City. During heavy precipitation or snowmelt events, water flows rapidly over impervious surfaces, picking up nitrogen compounds from vehicle emissions settled into dust, phosphorus from soil disturbance, and organic matter from urban landscaping before entering tributary streams feeding the lake. Then there's atmospheric deposition. Nitrogen oxides produced by regional vehicle traffic and distant industrial activity can travel through the atmosphere before settling directly onto the lake surface or into the surrounding basin. Over time, this creates a diffuse but continuous nutrient input that does not require a visible discharge point. Researchers at the UC Davis Tahoe Environmental Research Center have tracked these inputs as part of long-term water quality monitoring programs that began in the late 1960s. Historically, septic systems played a more direct role. Before modern sewer infrastructure was expanded around the basin, older developments relied on on-site wastewater disposal. Leakage from these systems contributed measurable nutrient loads to groundwater and nearshore zones. Although major infrastructure upgrades over the past several decades have reduced this source significantly, legacy impacts remain part of the lake's long-term nutrient history, especially in densely developed shoreline areas. Residential fertilizer use adds a more modern and distributed pressure. Even well-intentioned landscaping practices introduce nitrogen and phosphorus into runoff during irrigation or rainfall events. In a nutrient-poor system like Tahoe, these additions are disproportionately influential. What would be negligible in a eutrophic lake becomes ecologically meaningful here, where algae and phytoplankton populations respond quickly to small chemical changes. The biological response is subtle but measurable. Slight increases in nutrients can stimulate algal growth, particularly in nearshore zones where warmer temperatures and sunlight amplify productivity. This does not create sudden green water or visible algal blooms across the entire lake, but it does affect clarity measurements over time. Secchi disk readings, a standard method for measuring water transparency, have shown long-term variability since systematic monitoring began in 1968, with a general trend of decline from mid-20th century highs, though punctuated by recovery periods linked to dry or low runoff years. What makes this system particularly sensitive is its baseline. Because Tahoe is naturally nutrient poor, there is very little biological buffering capacity. In richer lakes, additional nitrogen or phosphorus is absorbed into existing ecological cycles without dramatic change. In Tahoe, the same input can shift growth dynamics among algae and plankton. This subtly alters how light travels through the water column. That is where clarity loss begins, the property that actually defines the lake. Fine sediment input and clarity loss mechanisms. Unlike bottles or tires that settle quickly and remain localized, fine sediment, often measured in microns, stays suspended in the water column, interacting directly with sunlight and reshaping how deep the lake appears. The process begins on land, in the surrounding watershed, where steep granite slopes meet rapidly developing urban edges. Roads are a major contributor, especially during dry months when vehicle traffic deposits oil residues, tire wear particles, and dust onto asphalt. When the first storms arrive, that accumulated layer is washed into storm drains and creeks. These systems, Trout Creek, Upper Truckee River, and others feeding the lake, act as high-speed conveyors, delivering sediment directly into nearshore zones. Construction activity adds another layer of input. Even regulated development disturbs soil that was previously stabilized by vegetation. In a basin where slopes can be steep and soils are easily eroded, exposed ground becomes a short-term sediment source. Despite modern erosion control measures, short-duration storm events can still mobilize significant material before containment systems fully respond. Wildfire activity has introduced a more recent and unpredictable source. Burn scars from regional fires leave behind hydrophobic soil layers that repel water, increasing surface runoff intensity during rainfall. Instead of being absorbed gradually, water flows rapidly over burned terrain, picking up ash, charred organic matter, and loosened mineral particles before entering tributaries. These post-fire runoff pulses can deliver concentrated sediment loads into the lake in a matter of hours or days, creating temporary but measurable drops in clarity. Once these particles reach the lake, their behavior changes depending on size and composition. Fine silt and clay do not settle quickly in cold, low-energy water. Instead, they remain suspended, distributed through currents and wind-driven mixing in nearshore zones. This suspended layer scatters incoming sunlight, reducing the depth to which light can penetrate. The result is not visible pollution in the traditional sense, but a reduction in transparency that is quantified through Secchi disk measurements, wherein white disks are lowered into the water until they disappear from view. Long-term monitoring by institutions such as the UC, Davis Tahoe Environmental Research Center, has recorded fluctuations in these clarity readings since systematic tracking began in 1968. While Lake Tahoe still ranks among the clearest large lakes in the world, its average clarity has declined from historic mid-20th century levels. Urban expansion around the basin amplifies this process by increasing impervious surface coverage, roads, rooftops, parking lots, and compacted soil areas that prevent water infiltration. During precipitation events, runoff moves faster and with greater force across these surfaces, reducing the time available for natural filtration. This increases both the volume and velocity of sediment reaching tributary systems. Hydrologically, the system is highly responsive. Snowmelt from the Sierra Nevada feeds a network of streams that can shift rapidly from low flow to high discharge within weeks. When combined with storm-driven runoff, these pulses create episodic sediment delivery events that temporarily degrade clarity, especially in shallow nearshore regions. This is also where recreational activity is most concentrated. But wait, the troubles don't end here. Invasive species and food web restructuring. In the cold, layered waters of Lake Tahoe, ecological change entered quietly through a species so small it was once seen as beneficial. In the 1960s, mysis shrimp, native to the Great Lakes region, were intentionally introduced into several western water systems as a potential food source for trout. In Tahoe, that decision would later be recognized as one of the most consequential ecological disruptions in the lake's modern history. At first, the logic seemed sound. Mysis diluviana migrate vertically through the water column, rising toward the surface at night and descending into deeper, darker layers during the day. Fish species such as kokanee salmon were expected to feed on them, strengthening the food web. But the system did not respond as predicted. Instead of becoming a direct food source, the shrimp settled into deeper cold water zones during daylight hours, zones where native zooplankton also depended on stable conditions. The result was competition at the wrong level. Native zooplankton species, particularly cladocerans and copepods that graze on phytoplankton, began to decline in key habitats. These microscopic grazers are critical in a low-nutrient lake like Lake Tahoe because they regulate algal growth by consuming suspended organic particles. When their populations shrink, algae face less biological control, subtly shifting how light passes through the water column. This shift did not produce an immediate visible change. There were no sudden algal blooms across the lake or dramatic ecological collapse. Instead, the effect unfolded gradually through altered energy transfer. Primary productivity began to reorganize, with changes in where and when planktonic organisms concentrated in the water column. Over time, this influenced the lake's optical properties, contributing to long-term variability in water clarity measurements tracked by researchers since the late 1960s. Field studies conducted by institutions such as the UC Davis Tahoe Environmental Research Center have documented how zooplankton abundance and distribution patterns changed following the mysis introduction. In particular, the separation between predator and prey layers in the water column became more pronounced. Mysis shrimp also introduced a form of ecological rerouting. Instead of serving primarily as prey for nearshore fish populations, they became part of a deep-water energy pathway, feeding and recycling organic material in colder, darker zones. This created a split in the lake's food web structure, one pathway operating near the surface where clarity is most visible, and another operating in deeper layers where biological activity is less obvious but still significant. Additional invasive species have compounded these effects over time, though none with the same system-wide impact as mysis. Aquatic plants such as Eurasian water milfoil, introduced through boat traffic, have established localized growth in shallow coves. These plants can alter habitat structure, slow water flow, and trap fine sediments, indirectly influencing nearshore clarity and ecosystem balance. Their spread is closely linked to recreational boating activity, which acts as a repeated vector for non-native species movement across water bodies. Boat-based transport has remained one of the most persistent introduction pathways. Even with modern inspection programs and cleaning requirements, microscopic organisms and plant fragments can attach to equipment and survive between launches. This transforms human recreation into a biological transfer mechanism. Climate change effects and regional environmental stressors. In the high basin of Lake Tahoe, climate change builds through temperature shifts measured in fractions of a degree, and through snow lines that climb higher each winter in the Sierra Nevada. For a system once governed almost entirely by predictable snowpack cycles, even small atmospheric changes begin to rewrite timing itself. The first signal is in snowpack behavior across the Sierra Nevada range, which feeds the lake through a network of tributaries like the Upper Truckee River and Trout Creek. Historically, deep winter snow acted as a natural reservoir, releasing meltwater gradually through late spring and early summer. But warming trends documented across the western United States have shifted this pattern toward earlier melt timing. Instead of sustained, slow inflow, the lake increasingly receives short, intense pulses of water earlier in the year, followed by longer dry periods. That change alters not just water level stability, but the internal rhythm of the entire basin. At the surface, lake levels respond in cycles, but beneath that surface, thermal structure begins to shift. Lake Tahoe is demictic, meaning it mixes seasonally, with stratification forming in summer and winter layers breaking down during turnover events. As air temperatures rise, the duration and strength of stratification can change. Warmer surface waters extend the period during which deep mixing is reduced, limiting oxygen exchange between surface and deeper layers. In a deep alpine lake that depends on balanced vertical circulation, even subtle changes in stratification timing can affect how nutrients are distributed through the water column. This internal chemistry is not static. Reduced mixing can influence oxygen availability in deeper zones, which in turn affects how organic material decomposes and how nutrients are recycled. In a low-nutrient system like Lake Tahoe, these processes are tightly constrained. Small shifts in oxygen and temperature gradients can alter microbial activity, changing how efficiently organic matter is broken down and how long particles remain suspended before settling. Then comes wildfire, a newer and more visible stressor. In recent decades, large fires in the broader Sierra Nevada region have increased in frequency and intensity, driven by hotter summers, earlier snowmelt, and extended dry seasons. Events such as the 2021 Calder Fire, which burned through parts of the Tahoe Basin, illustrate how fire no longer remains a distant mountain phenomenon. When these fires occur, they send atmospheric plumes containing ash, fine particulates, and dissolved organic carbon into surrounding watersheds. These materials settle onto the lake surface or wash in through tributaries during post-fire rainfall events. The effect of wildfire inputs is episodic but chemically significant. Ash contains nutrients such as nitrogen and phosphorus, which can temporarily increase biological productivity in otherwise nutrient-limited waters. At the same time, fine carbon particles and organic compounds can alter water color and light absorption, subtly reducing clarity in the short term. These inputs do not create permanent transformation on their own, but they add variability to an already sensitive system. What makes the situation more complex is the interaction between climate and human systems. Warmer conditions amplify evaporation rates, while altered precipitation patterns affect runoff intensity from developed shoreline areas. This means that climate stressors compound existing pressures from urbanization, land use change, and watershed modification. The result is a system that behaves less like a stable baseline and more like a shifting set of interacting variables. Researchers monitoring Lake Tahoe through long-term programs at institutions such as the UC Davis Tahoe Environmental Research Center have noted that variability itself is increasing. Not just changes in average conditions, but wider swings between wet and dry years, clearer and less clear seasons, stronger and weaker stratification cycles. In the long view, the lake is becoming less predictable. A system once defined by seasonal regularity is now shaped by overlapping climate signals. Warming air, shifting snow, wildfire chemistry, and altered hydrology, all interacting in ways that do not resolve into a single pattern. Instead, they accumulate into a new baseline defined by variability itself. Stability is no longer the default condition. Now, the system only occasionally returns to stability. For now, Lake Tahoe still looks untouched from the surface. Millions of visitors continue to arrive each year, drawn by the same deep blue water and alpine scenery that made the basin famous decades ago. But beneath that image, the lake is carrying the accumulated weight of continuous human pressure. Shoreline construction, road expansion, boat traffic, wastewater history, and runoff from heavily visited urban areas have gradually reshaped how water, sediment, and nutrients move through the system. Scientists are no longer focused on a single pollutant or isolated source of damage, but on the cumulative effect of decades of development layered onto one of North America's most sensitive alpine ecosystems. The danger is not a sudden collapse, but a slow shift in baseline conditions where clarity declines incrementally, habitats fragment quietly, and the environmental cost of recreation builds year after year until the lake no longer behaves the way it once did. The lake we all love and look at with awe needs our help to survive. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.